Okay, so hello and welcome to another week of NPTEL NOC 23MA14 Algebra 2 course. And I am one of the PMRFTAs for this course. My name is Shubhajit Das, and this is week 9. Okay, so as we keep doing every week, we will be solving problems based on the content of this week. So this week you have studied about tensor products of modules over a ring, and you know that a tensor product of modules is kind of like an operation on the collection of all modules, or more precisely, since you already know what categories are, it is an operation on the category of all modules over a ring, right? So you take a module M over a ring R and you take a module N over the ring R, then you can take their tensor product, which is given by M tensored over Rn, which is also an R module, provided the ring R is commutative. So you have studied this and investigated various properties of this concept. In particular, the definition of this concept is very beautiful, and as is the case for most special objects in mathematics, the tensor product is also given by a universal property. And so you also know what representable functors in category theory are. So that saying that the tensor product is given by a universal property is the same as saying that this tensor product object in the category of R modules, that is this object M tensored over Rn, represents some functor, right? Okay, so yeah, so after seeing its universal properties, you have also seen probably I know you have seen the construction of the tensor product, and both descriptions, both the external, that is a description using the universal property, and the internal construction, they are both, both come in handy. And the external description, the universal property description, is as good as the internal construction. This is what the Yoneda lemma says. Okay, anyways, so we won't be getting into such complications for the time being. Let us start solving problems one by one. Okay, so this is the first question. Yeah, I should use a different colored ink. So this is our first question. So we need to choose which of the following are correct. So we take Z, so the modules being considered here as Z5, Zn, Z7, Z8, Z6. Now we know that Z is a ring and Z5 is a module over the ring Z, right? Z5 is a Z module. Since Z is commutative, we need not mention whether it is a left module or a right module. So we take the module Z5 over the ring Z. And so the first question is about whether this is correct, that Z5 tensored over Z with Z7 is equal to 0. This is what we need to figure out, whether this is correct or not. So anyways, this was, I believe, solved in the video lectures. So we recall from the video lectures that Zn tensored over Z with Zm. So both Zn and Zm are Z modules, right? That is, they are abelian groups, and further there is an action of the base ring Z on these abelian groups, right? Which is a scalar multiplication of the module. So this as a Z module is actually isomorphic. This as a Z module is actually isomorphic to Z GCD of M comma N, right? And more generally, this is something that will be proving soon. For any commutative ring R, if we consider and ideals I comma j in R, if we consider the quotient R mod I, which also is which we already, so R is a R module, I is an R submodule of R, right? So we can take the quotient of R by I as a quotient module. It is also an R module, and R mod I tensored over R with R mod J. This is isomorphic to the R module R mod I plus J. So using either the first one or more generally the second one, we can right away see that option 1 is correct, because the GCD of 5 and 7 is equal to 1, right? So this is isomorphic to Z1, that is, in other words, it's isomorphic to Z quotiented by Z, which is 0. Now option 2, the GCD of 8 and 6 is 2, so option 2 is also correct. What about option 4? Option 4 is certainly not correct. And what about option 3? Option 3 says that Z5 tensored over Z with Z7 is isomorphic to Z, but we already saw that this is not true because the tensor product is 0, right? So thus clearly 1 and 2 are correct. A straight computation of GCD will give you the answer. Okay, so let us move on to the next problem. So it says that let n be a natural number, then we need to choose which of the following answers are correct. So first of all, Zn tensored over Z with Q is isomorphic to Q. Zn tensored over Z with Q is isomorphic to 0. Zn tensored over Z with Q mod Z is equal to 0. And finally, Zn tensored over Z with Q mod Z is isomorphic to Zn. So what about option B? Let's target option B. Now one of the properties of Zn is that Zn is a torsion module, right? It's a torsion Z module. On the other hand, so since Zn is a torsion Z module, we have some advantage here. Okay, so take any element, so we know that what was the internal construction of the tensor product. So the tensor product of two modules M and N over a ring R was obtained by first of all considering the free R module with basis M cross N, right? So we consider the direct sum of the copies of R indexed over the set M cross N, and in this free R module, what we did was we considered the submodule generated by certain generators, certain specific generators, and we took a quotient by this submodule and we obtained the tensor product, right? This was the construction of the this was our construction of the tensor product of two modules, right? And we know that since the free R module itself is generated by pairs M comma N, the collection of all pairs M comma N, where M is in capital M and N is in capital N, this forms a basis of my free R module. And since my tensor product is a quotient module of this, that is, there is an epimorphism of the free module onto the tensor product. Hence, the images of the basis elements, that so the image of M comma N will now be denoted in the tensor product as M tensored N. So this M tensored N, these are called elementary tensors, and they will generate the entire tensor product, right? So if Zn tensored over Z with Q is, if we need to show that this is 0, then it is sufficient to show that the elementary tensors are 0. So any elementary tensor in the Z module, Zn tensored over Z with Q. So any elementary tensor in this tensor product module is of the form some element of Zn, let's call it box A, tensored with some element of Q, let's take P over Q, right? Now this can be written as box A tensored with box A tensored with NP over NQ, right? Now since the tensor product is taken over Z, so one of the definitions, one of the properties of the tensor product is that you can switch scalars, right, between the first component and the second component of any elementary tensor. right? This was one of the properties of the tensor product. So scalars from the base ring are in this case z. So n is an element in z, it's a scalar, so we can switch the scalar to that side. So this is n times box A tensored with p over nq, but n times box A is 0, the class of 0, tensored with p over nq, right? And this is equal to 0, that is 0 tensored with 0. Why is this 0? Because again, because one of the properties of the elementary tensors, right? So you take box of 0 tensored with p over nq. This can be written as box of 0 tensored with p over nq plus box of 0 tensored with p over nq, because this elementary tensor is sort of bilinear in both components. It's sort of a bilinear in both components, right? And hence this equation is holding in an abelian group. You can cancel out and you get 0. So option B is correct, implies option A cannot be correct. Now what about option C? Is option C correct? So again, any elementary tensor in Zn tensored over Z with Q mod Z is of the form box A tensored with Z plus P over Q, right? And this can be written as box A tensored with box A tensored with n times Z plus P over nq, right? This is precisely the scalar multiplication by Z of the Z module Q mod Z, right? This is how you define this. So Q is a Z module. Again, Z contained in Q is a submodule, right? That is, it is closed under addition. It is closed under the operations of the module. So it is closed under addition and scalar multiplication by elements of Z. So Z is a Z submodule of Q, and then you can take the quotient Q mod Z. This is also, this quotient module is a Z module, and the scalar multiplication here is given by, so any scalar n times an element of the module is Z plus, is the class of n times that element, right? Exactly. I mean, any scalar times the class of any element is equal to the class of n times that element. This is what the well-defined scalar multiplication. This is what gives you the Z module structure on the quotient module, or generally the R module structure on any quotient R module, right? So again, since the tensor product is taken over Z, we can take n. Oops, sorry. Yeah. I hope, yeah. So we can take this. Let me just check. Yeah. So we can take the n on the other side. So we can get n box of Na tensored with Z plus P over nq, right? And this is equal to 0, right? So certainly any elementary tensor is 0. Yeah, so I should have written here. Hence Zn tensored over Z with Q is 0, and here hence Zn tensored over Z with Q mod Z is 0. So the interesting thing happening here is the fact that Zn is a torsion Z module, right? That is, element is a torsion element, and I mean, that is, every element is annihilated by some non-zero element, right? and what else? And the fact that both Q and Q mod Z are divisible, right? Both Q and Q mod Z are divisible Z modules. So this is what is actually happening here. So yeah, so certainly C is also correct, which implies that D cannot be correct, right? So let us move on to the next problem. So we again need to choose which of the following are correct. First of all, Q tensored over Z with Q is isomorphic to Q. B says Q tensored over Z with Q is equal to 0. C says Q mod Z tensored over Z with Q mod Z is isomorphic to Q mod Z. And D says that Q mod Z tensored over Z with Q mod Z is equal to 0. Okay. Now let us first of all look at E. Now we can prove this using the universal property of the tensor product, that Q tensored over Z with Q is isomorphic to Q. This is indeed correct. But a better way to understand this is as follows. So you know what an epimorphism is in a category, right? An epimorphism in a category is precisely a morphism that is right cancelable, right? So it is a morphism from one object into another object, which is a right cancelable morphism from one object into another object, and that is called an epimorphism from one object into another object, from the first object into the second object. So this is what an epimorphism is. And so there are a couple of things that you need to check here. So I'll just state this. So A is correct. So steps to see that A is correct. Either you can use the universal property, that would be an easier way. But since, but this I believe is a better way. I mean, this I believe is a good learning point for you. So the steps are, firstly you check that the inclusion Z of Z into Q is an epimorphism. Precisely the inclusion of Z into Q gives you the structure of a Z module, right? Q is a Q module, we already know, but by restriction of scalars we can say that Q is also a Z module along this inclusion. So this is an epimorphism. So this is an, so the inclusion of the inclusion of Z into Q is an epimorphism in the category of rings and ring homomorphisms. Step 2 is to observe, is to check that in any category a morphism F, so yeah, in any category a morphism from A into B F is an epimorphism if and only if you take this square, so A to B F F, so maybe I need some space here. So this is B, this is the identity map on B, this is the identity arrow on the object B. This square is a push out square. Okay, and step 3 is to observe that push outs in the category of rings is given by tensor product. That is, if you take A to B and if you take, yeah, so sorry, I should be very precise here. Yeah, so if you take A to B a map and A to C a map, and if you try to obtain the push out of this diagram, then the push out, so you have a map from A to B which makes B into an A module, and you have a mapping of A into C which makes C into an A module. So both B and C in the category of commutative rings. Yeah. So B is an A module, C is an A module, and therefore you can take their tensor product over A, which is again an A module, B tensored over A C, right? And you have a canonical mapping of C into this, and you have a canonical mapping of B into this. You check that this is a, so let's say this is F, oops, Sorry, I don't know what is happening. Technical problems with the device. So let's call this F. Oops. Let's call this F. Let's call this G. You have a canonical mapping of C into this. You have a canonical mapping of B into this, right? And yeah. So what I was saying is. Yeah, what I was saying is this is a push out square. Square in the category of rings. I mean commutative rings. Okay, and once you know this, therefore what you have is yeah, so I need to make some space. Once you have this, therefore, so you have the inclusion of Z into Q. This is an epimorphism, and you have an inclusion of Z into Q. This is again an epimorphism. So the push out will be, as you know, Q tensored over Z with Q. But since this is an epimorphism, so everything is happening in the category of rings, right? So yeah, so whenever I say that I am taking tensor product of the, so precisely if A is commutative B and C, and you have a mapping of A into B, and you have a mapping of, I mean you have a ring homomorphism of A into B, and you have a ring homomorphism of A into C. Then B and C are actually not only just A modules, but they are A algebras, right? That is, these are rings which additionally have an A module structure, such that the ring structure and the A module structure are compatible with each other, right? So these are A algebras, and you, as a tensor product, we are taking B tensored over A with C as a tensor product of the modules of the A modules B and C, but this can also be equipped with an A algebra structure, right? That is, in part, what I want to say is this can be equipped with a ring structure, right? I believe you have seen this. So this the push out is this Z algebra, that is this ring Q tensored over Z with Q, but this is again isomorphic to Q, precisely because this is an epimorphism. This so its push out along itself will be Q, right? I mean the map should be identity, right? So that finishes the proof. Okay, so Q tensored over Z with Q and Q are isomorphic as rings, and hence they are also isomorphic as Z modules because their underlying abelian groups are isomorphic, right? Now so A is correct. Now just to give a, I mean just to make sure that we are on the same page, I will also define what is a push out square in case you don't know. So this is just a definition, category theoretic definition, a push out square. So a push out square is a special kind of so yeah, so a push out square is a special kind of co-limit in a category. Okay, so given a category script C and a diagram of objects and arrows and a diagram, so you have A here, A to B you have a morphism, and A to C you have a morphism. Okay, the push out of this diagram, if it exists, is a triple P if hat g hat. Okay, so what are the maps if hat and g hat? So P is an object in the category. If hat is a map from C into P, right? And G hat is a morphism, that is an arrow. G hat is an arrow of B into P, such that the given square will commute, such that so yeah, I need more space. Such that this square commutes. So such that A to B you have an arrow, and A to C you have an arrow. So this is F, this is G. And this is P. You have an arrow of C into P, and you have an arrow of B into P. I mean, there exists an arrow. If the push out exists, then this will exist. Dotted arrow of B into P and a dotted arrow of C into P. So this is F hat and this is G hat, right? Such that this square commutes yeah, just a minute. Says that this square is a commutative square, right? This square is a commutative square, and this triple P F hat G hat is the universal triple with respect to this property. That is, it is universal. It has this universal property. It is universal among all triples with the same property, right? That is, it is a universal triple with respect to this property. Or this is a triple which is universal to the given diagram, right? So which means that, and for any, yeah, so I should write things such that this square commutes and what else, and for any triple Q, let's say H from C into Q, and K from B into Q, right? Triple, such that, so you have this A to B, you have A to C. So suppose this is Q, you have a map C to Q, H, and you have a map P to Q, K, right? Such that this commutes. There exists, if this be the case, then there exists a unique arrow, a unique morphism exists from the push out P into Q, right? So this is your push out. So this is F, this is G, this is F hat, this is G hat, right? From P into Q you get a map. So let's denote it by a different color, maybe black. Yeah, just a minute. Yeah, it's not very clear actually. Yeah, Now I guess the picture will look better. So unique arrow, let's call this arrow I don't know, let's call this arrow q. Let's call this arrow q. So this arrow is q, unique arrow is q, such that all the triangles will come in, such that such that q composed with f hat is equal to h. That is, in other words, q composed with g hat is equal to k. That is, in other words, what I am saying here is that this is the push out is a triple set making the diagram commutative, such that for any arbitrary triple which makes the diagram commutative, that arbitrary triple factors through the push out, right? I mean uniquely, yeah. So the push out is a triple which makes the diagram commutative and is such that for any arbitrary triple which makes the diagram commutative, the arbitrary triple will factor uniquely to the push out triple. Okay. It will factor uniquely to the push out triple via a unique map from the push out to Q. Okay, so this is the definition of push outs in a category, and there are various examples of push outs in different categories. For example, you can check that in the category of sets and mappings, the push out is given by unions of sets. On the other hand, in the category of let's say so the push out always has the description that you first take the co-product of the two objects P and C and you take a quotient object of it. Okay, that is, there is an epimorphism of the co-product into some into the push out object. Okay, so the push out object is a quotient object of the co-product of B and C. This is precisely the idea. So that finishes the proof. So this is isomorphic to this as rings, and hence as Z modules. That finishes the proof. And alternatively, if you want to avoid category theory stuff, you can, still universal property is also something from category theory. Alternatively, you can just use the universal property. The fact that the tensor product actually represents a functor, right? That property, universal property of the tensor product. Okay, right. So certainly A is correct, and since A is correct, B cannot be correct. What about option C and option D? So we need to figure out whether the tensor product of the abelian group Q mod Z with itself, right? Whether the tensor product of these two Z modules is 0 or it is equal to Q mod Z. So yeah, I need more space. So just a minute. So now we come to, so let's first investigate D. Let's see if D is correct. So to see that the tensor product is 0, we can just work with elementary tensors and show that elementary tensors is 0, and therefore we have the entire tensor product will be 0. So actually D is correct. Okay, an elementary tensor in the tensor product of the quotient Z module, this was Z with Q mod Z, is of the form z plus p over q tensored with z plus let's say m over n. But the interesting thing here is that since q mod z is divisible, so what you can do here is so since q mod z is divisible and q mod z is again torsion, so what you can do here is this can be written as z plus p over, let's say, yeah, so this is equal to n times z plus p over nq, right? Tensored with tensored with right. So what I was thinking is yeah, yeah, so this can be written as z plus m over n, and again since n is a scalar in the base ring z, so you can bring it to the second component. So this tensored with n times z plus m over n, which is equal to z plus p over nq tensored with z plus m, but z plus m is precisely your 0, is the identity element of q mod z, so this is 0, right? Hence q mod z tensored over z with q mod z is actually equal to 0. So certainly option D is correct, which implies that option C is incorrect, right? Okay, so let us move on to our next problem. Okay, so I need to make spaces again. Maybe I do need some more space. This seems fine. Okay. So again we need to figure out which of the following options are correct. First of all, so you take this abelian group of real numbers, that is the z module of real numbers. So r tensored over z with q is isomorphic to q. Second one says r tensored over z with q is isomorphic to r. Third one says r tensored over z with q is isomorphic to 0. And fourth one says r tensored over z with q is isomorphic to z. Now just by looking at it, you can already discard two, you can already discard two options, right? So if you observe carefully, then you have this inclusion of z into r, right? And you know that q is a z module, right? So you know that once you have this once you have a mapping ring map of one ring into another ring, associated to this ring map from one ring to another ring, associated to this ring map are two functors in opposite directions, and they form an adjoint pair of functors. One of them is precisely your scalars functors, and the other one is the restriction of scalars functor, right? But and there is an adjunction between both of them, but probably okay. So let me ask you, Chaitra. Hi. Yeah. So did you study adjoint functors in the category theory course? Was it done? Oh, okay, fine. So you know that if you take a ring map of a ring A into a ring B, then associated to this ring map are two functors, right? There is an adjoint pair of functors, right? From the category MA to the category MB, where MA is a category of A modules and MB is a category of B modules. You have the extension of scalars functors, which takes any module M and what it does is it sends M to M tensored over A with B, right? This is a B module, right? Are you aware of this? Extension of scalars. Sorry, I couldn't get you. Anyways, so there is also another functor in the opposite direction, which is the restriction of scalars functors, right? And so what is restriction of scalars? If you take so F is a ring map of A into B. Now if N is a B module, then you can restrict the scalars and you can get an A module. If N is a B module, then N is automatically an A module, right? So N is a B module. So probably we won't be needing so much in this problem, but give a full description of the thing. So assume N is a B module. What does it mean? It means that N is an abelian group together with a together with a scalar multiplication of B on N, right? That is, there is a mapping of B cross N into N, right? So B comma N gets mapped onto B dot N. So this is your action of B on N, linear action. Now N can also be thought of as an A module, right? So N is already an abelian group. What else do you need to make it an A module? You just need scalar multiplication by the elements of A. So you need a mapping of A cross N into N. And how do you define this mapping? So A dot an element of N, you define it to be FA dot N, right? FA is an element of B, and here you are using the B module structure of N. You can check that N is indeed an A module. Okay. So whenever you have a B module in MB, whenever you have an object in this category, you map it using the restriction of scalars functors to an object in the category MA. Okay. So there are two functors these are two functors in opposite directions, and they are adjoint to each other. The extension of scalars functor, that is this tensor functor, is left adjoint to the restriction of scalars functors. You can check this in case you didn't know this, but anyway, so this is not a, this is probably too much for the problem, but at least we don't need the adjunction. What we need here is just the extension of scalars functor. So if it was not clear, let me just give you a quick description of this. So you have this functor tensored over A with B. What does it do? It maps any A module M onto the module M tensored over A with B. So first of all, we don't even know whether M tensored over A with B is actually a B module. For the time being, we just know that it is an A module, right? Since there is a ring map of A into B, B is an A module, and since M is an A module, so we can take the tensor product over A to get the A module M tensored over A with B. But this M tensored over A with B actually has a structure of a B module, if you see clearly or observe clearly. So what is the structure? So take any element in M tensored over A with B. You know that it is a sum of elementary tensors, right? So to define an action of B on this, it is enough to just define an action on a generator, right? So take any element M tensored with B, and you want to define this multiplication with some scalar multiplication with some scalar which is from B. And what should you define it to be, Chatra? So you want an element of M tensored over A with B, right? What should you define this scalar multiplication to be? Yes, M tensored with B, B dash. This is where you are using the fact that B is actually an A algebra. B is, in particular, B is a ring. This is what you are using. And you can check that this makes M tensored over A with B again into a B module. So that what we have done here is actually does make sense. It is not nonsense. And again you have this map from N to N tensored over A with B. And since it's a functor, it should map arrows to arrows as well. So take any module map from M into N, you map it onto the arrow if tensored with 1b. Is it clear, Chaitra, what is if tensored with 1b? What is this? Yeah, so and you also know, right, how it is induced. So you have this map from m cross b into n tensored over a with b, which sends m comma little b onto if of m comma little b, sorry, tensored with little b. And you can check that this map is a bilinear. So using the universal property of the tensor product, so you know that this map from m cross b to m tensored over a with b, this is the universal bilinear map out of m cross b. So any other bilinear map from m cross b will factor uniquely through this one, which means that you get a map from the tensor product of m and b into the tensor product of n and b, and this map is precisely your f tensored 1b. What does it do? It takes the pair m comma little b and sends or maps the pair onto fm tensored with b, little b. Okay, so at least we have defined the assignment for the functor. We have defined the data of the functor. You can check that this data actually satisfies the axioms of a functor, which makes this extension of scalars actually into a functor. This is called the extension of scalars functor. And the point is this: why is it called extension of scalars? Because usually in such situations you would be taking the map f to be a ring inclusion, right? So a is thought, you can think of a as a subring of b, and what you have done is you take an a module and you have extended, you have defined a module which is now a b module, right? So in a way you have extended your scalars, right? You can take more scalars and multiply them with the elements of your module. That is why this is called the extension of scalars functors. Now why am I talking about it here? It's because right away, looking at this 4 options, you can right away discard 2 of them. Okay, so what are the 2? They are precisely these 2. So first of all, you take this inclusion of z into r, right? This is again ring inclusion, it's a ring homomorphism, and you take the extension of scalars functor from mz into mr, right? What does it do? It takes any, so it is defined as we have given here. In particular, you take the z module q and using the extension of scalars functor, so extension of scalars functor, you map it to q tensored over z with r, right? Now what is this? This is an r module. This is a module over the real numbers. In other words, this is a real vector space, right? Isn't it? So if it actually is a real vector space, can you tell me why this is incorrect? Why can't this vector space, so q tensored over z with r is the same as r tensored over z with q. Okay, there's no doubt about that. They are canonically isomorphic, but can you tell me if, so r tensored over z with q is actually a real vector space. If that is the case, why can't it be isomorphic to q as a z module? I'm speaking of as z modules. But r tensored over z with q is not only just a z module, you know, it's a real vector space. So why can't it be isomorphic to q as a z module? Can you give me a small quick one-line argument? So I'll give you maybe 2 minutes to think. So do you have an argument? Chatra? But you understood what I said, right? That R tensor over Z with Q is a real vector space. That much is okay, right? Okay. Now, suppose these two are isomorphic. Indeed, R tensor over Z with Q is isomorphic to Q. What would that mean in particular? That would mean that R tensor over Z with Q as a real vector space, at least the underlying set is non-trivial, right? I mean, as a real vector space, it's non-zero. Now, if a real vector space is non-zero, can it be countable as a set? No, right? But Q on the other hand is countable. So that this is not correct, and in the same, using the same line of reasoning, you can say this is also incorrect because Z is countable. The I mean the one on the left hand, the tensor product is not countable. Now tell me which of these two will be correct, B and C. Okay, B will be correct, and why is that? Why is that the case? So there are various ways to reason about this. If you know localizations, maybe we could give a very shorter argument. But what is the best way? What is the sort of the canonical way to do such things to show that a tensor product is isomorphic to something? What should you do? Just what is the single word that you will be using here? In one word, what is it? What is the property of the tensor product that we are going to use? We are going to use the, what property of the tensor product are we going to use to, okay, fine, forget my line of reasoning. How will you be showing that B is correct? You said that B is correct, so how will you be showing that B is actually correct? So to show that two objects are isomorphic, you need to produce a morphism from one object to another one, which is an isomorphism, right? Projection kind of map. Okay, that's a good thing to say. But so what you are suggesting is you are going to use a map like this: x tensored with y maps to x. This is what you are talking about. But tell me something, Chatra. Is this map well defined? First of all, it could happen in that, since the tensor product is a quotient of a module, it's a quotient of the free module generated, I mean with basis r cross q, right? Since it's a quotient, two elements can get identified, right? It could happen that x tensored y is the same as, let's say, a tensored b. In that case, the map won't be well defined, right? Where a and x are different. In that case, the map can't be well defined, right? So the projection will not work here. So what isomorphism of R tensor over Z with Q into R are you going to take? Okay, so what I was saying is, to get maps out of the tensor product, what property of the tensor product do we use generally? We use the universal property, right? Isn't it? So we take a map from R cross. So recall the definition, universal property of the tensor product. How was it actually defined? A tensor product of two modules is a way of capturing bilinear maps from their Cartesian product, right? That is what a tensor product does, right? It measures bilinear maps. In other words, if M and N are R modules, then the tensor product of M and N is a pair T comma G, where T is an R module and G is a bilinear mapping of M cross N into T, which is universal among all bilinear maps from M cross N, in the sense that for any arbitrary bilinear map from M cross N into some module, let's say P, this bilinear map will factor uniquely through the universal one. That is, there is a unique A module map, A linear map from the tensor product T into P, which makes that particular triangle commute, right? That is what the definition, universal property, which is as good as a definition. As category theory says, universal properties are enough to know objects. You don't need to even know how the object looks internally, that is how it is, what is it composed of from an internal point of view. It is enough to just know the maps out of this object or the maps going into this object. So anyways, so the universal property is as good as a definition. So we need to first of all define a bilinear map from R cross Q to R. So we take an element x comma y, let's say y is a rational number, very bad notation, but yeah, okay. So where should we send this pair to? What do you think? Where should we send this pair to? Yes, x into y, obvious, x times y. Now check that this map is Z bilinear. Check that this map is Z bilinear, which means that it is a mapping of the product into this second module such that so it is a mapping of the product into this second module which is linear in both coordinates, right? That is what bilinearity means. So check that this is actually bilinear in both components, and that precisely happens because R is a ring and it has distributive law. Okay, so check that this map is Z bilinear, hence you get a map, get an arrow from R tensored over Z with Q into R, right? What does this, so let's call the original map F, this is F hat. It takes x tensored y, an elementary scalar, a generator in this Z module, to xy. Okay. And but this is not enough, right? You have obtained a morphism of R tensored over ZQ into R, but to check that this morphism is an isomorphism, what do you need to check? What do you need to find? To show that a morphism is an isomorphism, to show that a particular morphism is an isomorphism, what do you need to do? You need to check that the morphism is invertible, right? That is, there it has an inverse morphism, it has a morphism in the opposite direction. So you need to find a morphism of R into R tensored over Z with Q. So define the map from R into R tensored over Z with Q. What map should we take here, Chaitra? So defining this is easy. We don't even need to use universal property, because universal property of tensor product actually gives you the idea of maps out of the tensor product, not into the tensor product. Okay. So to define a mapping of R into R tensored over Z with Q, define a morphism, it is enough to just define it, I mean usually in the usual way. So where should you send A to? A on to? A should go to? A tensor 0, okay. 8, if you take 8, so you know this property of the tensor product, right? X tensor with, I mean elementary tensors. Yeah, exactly. So then we would be having the 0 map, and we know that the 0 map is clearly not invertible. So where should you send this to? You should send it to A tensored with what? Exactly, A tensored with 1. And you check that this map is a linear. It's a map of modules. It's a morphism of modules. And sorry, not A, Z. The base ring is Z here. Z linear. And fine. So let's call this map G hat. Finally, what you see is F hat composed with G hat is equal to the identity map on R. That's clear, right? Because if you take little a in R, you send it via G hat to A tensored with 1. Again, you send it via F hat to R. What you get is A. And you also have G hat composed with F hat is equal to, so you take x tensor y, you send it to xy, again you send it to xy tensored with, okay, there's something wrong here, right? Is it? Yeah, this needs some explanation. I'm sorry. There's a reason we are using R and Q here. I need to make a little bit of, I need space. Yeah, so one composition is identity, that is very clear. But what about the other one? Yeah. Now G hat composed with F hat, this map applied on an element in the tensor product x tensored with, so I'll be writing an element of Q as P over Q. Okay, so this is equal to, as you know, x, so P over Q is a rational number, that is why I wrote P over Q. So this is equal to G hat applied on xp over Q, which is equal to xp over Q tensored with 1, right? But you actually need to see that this is equal to x tensored with P over Q, right? So this can be written as, see, P over Q, P and Q are integers, right? So in particular, since P is an integer, you know that you can switch, I mean you can change the position of the scalar in the tensor, in the elementary tensor. So you can write this as x over Q tensored with P. This much is clear. Now, yeah, I'm still not sure how to bring P over Q here. Did I do something wrong? You still don't have a over Q there, right? Isn't it? So my question is this: why is x tensored with P over Q the same as x over Q tensored with P? This is what we are stuck in. I think I took the right maps. Why this two should be equal? Have you studied flat modules, by the way? Was it covered? Okay, okay, fine. So why is x tensored with P over Q equal to this? Certainly we can't take x to that side. We only can switch integers. So why is this the same? So this should be 1 over Q, right? I mean 1 over Q. Oh. Yes. Actually the point is that this R tensor over Z with Q, it's a Z module that you know, but again by extension of scalars you also know that this is a Q module, right? Yeah, this is a Q module, but then again I kind of run into an issue. I don't know why are these two equal. Okay, let's sort of give some time to it. If I can do it, we'll see. But anyways, we are just left showing that this is equal to x. Yeah, you have something. Yeah, R tensored with over Z with Q is an R vector space and a Q vector space actually as well, right? Because Q is a subfield of R. No, there's an issue here. The point is this tensoring thing is happening over Z, right? Not over Q, right? That is why we can see switch scalars, switch integer scalars. That much, that is all that we are allowed to do. So what I was thinking is it's a Q module. It's a Q module on both sides. I mean, it's a Q bi module. It's a left Q module as well as a right Q module. So probably I was thinking I could sort of define, I mean, I could sort of take 1 over Q times X tensor P and then take it to the other side. But yeah, that is not, I mean, that is not right away correct. So anyways, let's give it some time. We just need to check that this is X tensored with P over Q. Yeah, we need to check that. Actually, is it difficult? Because is it? X tensored with 1, you can write it as X tensored with, so this is precisely Q times X tensored with 1 over Q, right? This we know, and therefore X tensored with 1, I mean 1 by Q times this is equal to X tensored with 1 over Q, right? And at the same time X over Q tensored with 1 times Q is equal to X tensored with 1, again for the same reason. Yes, then we are done. Yeah, so what I am saying here is this. I actually don't, since I'm sort of a category theorist, I mean I am, and that is why I don't really like working with elements and computations, and that is why I'm very poor in this kind of stuff. But yeah, so what I was suggesting you is, but yeah, but computations are really important in mathematics. Very, I should be serious about all this. Yeah, so X over Q tensored with P. So yeah, so what we need to show is that this equality holds, right? Right? Yeah, so X over Q tensored with P times Q is equal to X tensored with P. Is this clear? Why? Because you know that the tensor product is linear in both components. So Q times this, you can write this as, I mean, you know that X tensored with Ry is equal to Rx tensored with Rx tensored with Y, which is equal to R times X tensored with Y. That is what we are using here. So this therefore implies that X over Q tensored with P is equal to 1 by Q times X tensored with P. And again, you know that X tensored with P over Q times Q is equal to X tensored with P, and therefore X tensored with P over Q is equal to 1 by Q times X tensored with P. Okay. Yeah, here we are using something that I should be very clear about. See, I have taken 1 over Q times X tensored with P, right? But we know that a priori this R tensored over Z with Q, this is just a Z module. We don't know whether it's a Q module. We don't know whether we can multiply by scalars from Q, right? But it, by extension of scalars, we know that this is actually a Q module. So that 1 over Q times X tensored with P makes sense, right? Right, this is we define it to be 1 over Qx tensored with P, isn't it? Yeah, so that is why we can do this. We can take the q on the other side. That is why what I'm saying. Yeah, so anyways, so this shows the equality of the two. Okay, so yeah, so what we have is this is uh, this is true for all elementary scalars, all generators of this tensor product, which implies that this is true on the entire tensor product, that this is equal to 1 on R tensored over Z with Q. Hence, this map from R tensored over Z with Q into R, this is actually an isomorphism. If hat is actually an isomorphism. This arrow is an isomorphism. And that finishes this proof. Okay, let us move on to next problem. Next one is easy, not difficult. Very easy. It will take only 3 minutes. Yeah, so we have taken two different Z modules, two different tensor products actually. One of them is A, which is Z tensored over Z with Z5, and B is 5Z tensored over Z with Z5. We just need to choose the correct answers. So which of these will be correct? What do you think? Probably you said. Okay, A will be correct. Can you think a bit more? So if you consider A, I mean the module A, so A is Z tensored over Z with Z5, right? So to show that a module is 0, it is enough to show that every elementary scalar, every generator, you know that this so you know that this I mean the tensor product is uh, what was I saying? Yeah, the tensor product is generated by all x tensored with y, right? Every element is a sum of elementary tensors. So to show that this tensor product is 0, it is enough to show that the elementary tensors are 0, right? So an elementary tensor, okay, well, yeah, we don't even need to show, sorry, this won't be 0. I'm sorry, I just need to check that 5 tensored with 2 is 0 or not. So 5 tensored with, so in A, 5 tensored with 2 can also be written as 5 times 1 tensored with 2, right? 1 is an element of Z, right? And therefore we can write this, we can make this decomposition, and this is therefore equal to 1 tensored with 5 times 2, right? Isn't it? And this is 1 tensored with 0, because 5 times Z5 is a torsion Z module, right? It's a torsion abelian group which is annihilated by the integer 5 in particular. So 5 times anything will be 0. So this is 1 tensored with 0, which is 0. On the other hand, you cannot do the same thing in B. In B, 5 tensored with 2, you can never write it as 5.1 tensored with 2. Why? Because if you look at B, B is 5Z tensored with Z5, right? Right? Now in 5, 1 is not an element in 5Z. You cannot write this to be equal to 1 tensored with 5 times 2, right? This, because 1 is not an element in the first module. So you can't do this. But that doesn't, by the way, that doesn't mean that it can't be 0. This is something that you have to check. So I'll leave this for homework, maybe. So yeah, so check that 5 tensored with 2 is not equal to 0 in B. You can't take 5 on the other side doesn't mean that it won't be 0. There is a specific reason why it can't be 0. Okay, so so yeah. So do you have an argument for this one right away, or you want to think about this back at home? Okay, but please do, this is important. Showing that some elementary tensor is 0 is easy, and showing that some elementary tensor is non-zero is actually difficult. It is actually difficult. Okay, so what I am suggesting here is which one is correct? D is correct, right? Yeah, D will be correct. All other options are wrong therefore. So this was all about question 5. Let's come to question 6. Okay. So let S be a subset of R. I mean, it be a subring of a ring R such that they have the same common identity element. Usually by subring we mean this, that the identity element of R should be in S. Now we need to choose which of the following are correct. So first of all, R is a right S module. Is it correct? So you have an inclusion of S into R. You have a, forget inclusion, you have a mapping. You have a morphism of S into R. You have a morphism of S into R. So is R a right S module? Is option A correct? Why? Because by restriction of scalars, right? You know that R itself is an R module, right? You know that everything is a module over itself. The submodules of that module are precisely the ideals of the ring, provided the ring is commutative and all that. Otherwise, you will only have left ideals or right ideals. Anyways, forget what I'm saying. So R is a module over R, and therefore by restriction of scalars, R is a module over S. So in particular, you can actually put the module structure from the right, that is R is a right S module. So option A is correct. What about option B? R tensored over S with S is a left R module. Is this correct or is this wrong? So A is correct, as R is a right S module by restriction of scalars. Is B correct? R tensored over S with S is a left R module. Is this correct? Sorry. Yeah, it is obviously an S module. In fact, R tensored over S. Do you know this, that for a commutative ring A, for any ring, but usually it's done for commutative rings. For any commutative ring A, if M is an A module, then M tensored over A with A is isomorphic to M. Do you know this? Oh, this is a canonical isomorphism, and you can actually define the maps. So using the universal property, you have a mapping of this into M. You send M comma A onto M A, maybe let's say, or AM, doesn't matter because A is commutative. Even if A is not commutative, just assuming M is a right R module, then these are isomorphic as abelian groups. And on the opposite, in the opposite direction, you have a mapping of M into M tensored over A with A. You send M to M tensored with 1. You can check that these two arrows are actually inverses of each other. Okay, these two arrows are actually inverses of each other. That is, this arrow is an isomorphism, and so is this one. So they are canonically isomorphic actually. So M tensored over A with A is isomorphic to M as an A module. So if you take R tensored over S with S, then it is actually isomorphic to R as an S module. So is this actually a left R module? You don't need to get to all those isomorphisms actually. I mean, you don't even need to check that this is or see that, or use the fact that this is isomorphic to R as an S module. You can do it very clear, I mean very easily. Forget this for the time being. Again, by this is just extension of scalars, right, isn't it? So S to R you have this map. So from the module category MS into the module category MR you have this extension of scalars functor. S is a module over itself. You map it to R tensored over S with S, isn't it? This will be a left R module, right? And forget, I mean, these are still complicating stuff. You can just define the structure as follows. So you need to define a map from R cross R tensored over S to S, tensored over S with S to R, sorry, to R tensored over S with S. R tensored over S with S should be a left R module. So what map should you define? So R comma little r prime tensored with S should get mapped onto R prime tensored with S, the usual one that makes it into a left R module. Okay, so B is again correct. As R tensored over S. Okay, so as this mapping, this morphism from this into this, which sends R comma R prime tensored S to R prime tensored S, induces a module structure, induces a left R module structure. On R tensored over S with S. Now tell me, so B is correct, A is correct, B is correct. Is C correct? Certainly we know that these two are isomorphic. I mean R tensored over S with S and R, they are isomorphic as they are isomorphic as S modules, but they are actually isomorphic as left R modules as well, not only just left S modules. Indeed, the isomorphism that I was talking about, this map R tensored over S with S to R, sending R tensored with little s to RS, you can check that this map is not only just S linear, this is an isomorphism. This is not only just S linear, this will actually be R linear. Okay. And that is precisely because of the way the R linear structure on the R module structure on the domain has been defined. So let's call this map to be F. So F of R prime dot R tensored S. We define this to be F of R prime R tensored S. This was the module structure on on the domain, and this is equal to R prime R S, right? Just use associativity in the ring R to get R prime RS, which is R prime times F of R tensored with S, which says that this isomorphism is actually an R linear isomorphism. Okay. Is it okay? Yeah, if you have questions, you can ask me. Always. You can just stop me and ask me. Yeah. So, is an isomorphism of left R modules. Now, since C is correct, D cannot be correct, right? Because there is no guarantee that a ring will always be isomorphic to a subring of itself. And in fact, if you observe carefully, if S is a subring of R, then it's not necessary that S will be an R module, right? There is no guarantee to that. For example, Z is a subring of the real numbers, but Z is not a module over the real numbers, right? Because otherwise that would mean Z would be a vector space over reals, which would mean that Z had to be uncountable, but that is not the case. So what I'm saying is this is incorrect. This is not correct. Because if this were correct, then this would imply S is isomorphic to R as left R modules. Okay, easy reasoning. Okay, let's come to problem 7. This is a good one. I mean, you just have to use a universal property, that's all. But it's a bit of time consuming. So let's see if we can do it quickly. What is this? Yeah. So which of the so R is a commutative ring. I and J are ideals of R, which we need to figure out which of the following are correct. So what do you think? Which of these will be correct? So is A correct? R tensored over R with I is isomorphic to R. A is incorrect actually, as because we saw just now that so R is an R module. Any ideal of R is a submodule of this R module R, which means that it's a module over R in its own right. You can take the tensor product of R with I, and you know that R tensored over R with any R module, not just I, any R module is always isomorphic to I, right, as R modules, isn't it? This is what we saw just now, right? So if it is isomorphic to I, and assuming that A were correct, that would mean R is isomorphic to the submodule I. Any ring is isomorphic to its ideal as modules over the ring. That is again fallacy, right? That is not correct, right? So this is incorrect. Is it clear? Is the reasoning clear? Yeah. So again B is incorrect clearly, because there's no guarantee that I will be isomorphic to the quotient R mod I. There's no guarantee at all. For example, you can just take Z. You can just take the ideal 5Z, let's say. You can take the corresponding quotient, which is Z5. These two are clearly not isomorphic, right? One is finite, one is infinite. So the same line of reasoning says that this is incorrect. What about option C? Yeah, option C we just saw is correct. What about option D? So C is correct. And what about option D? Will D be correct or not? In fact, you have already seen an important instance of this. So I covered this back at the beginning of this session. So you know that Zm tensored over Z with Zn as a Z module, as an abelian group. This is isomorphic to what? Z. Exactly. And this D actually generalizes this, right? So you have Z mod Mz. Mz is I, tensored over Z with Z mod Nz. Nz is J. This is isomorphic to Z mod I plus J. So Mz plus Nz, which is the ideal generated by Mz and Nz. In other words, is the ideal generated by M and N. That is the ideal generated by the GCD. So it's Z mod GCD of M. Okay, so this is a generalization of that. And what was I going to say? Yeah, we need to prove this. Sorry. Yeah, so how do you show that? Again, to show that a tensor product is isomorphic to something, you can use the universal property. You can use the fact that this tensor product is actually an object that represents a functor. I guess that definition was not covered, but okay, forget that. You can use the universal property right away. So we need a map from this tensor product into R mod I plus J, right? So you first of all define an R bilinear mapping of the product into R mod I plus J. So take any element I plus R, take any element J plus S. Where should we map this to? Okay, let's see if R into S actually works. R into S plus I plus J. Okay. So tell me something, is this bilinear? Is this R bilinear? So we have defined a mapping f of this into this. Is this R bilinear? It is, right? You can say it quickly, because f of I plus, let's say, a times I plus r comma j plus s, this is equal to a r s plus I plus j, right? And you can take a out of this again. If you multiply a in the second component, you can take this, do the same thing, and it is clearly additive in both components. So this is why you took r times s, right? If you would have taken r plus s, that won't work. Okay. Is it okay? Because if you would have taken r plus s, that won't be actually multiplicative, scalar multiplicative in both components, so that won't work. The product thing will work. So yeah, so this is R bilinear, induces a map from R mod I tensored over R with R mod J into R mod I plus J. This, let's call this map f hat. It maps any elementary tensor I plus little r tensored with j plus little s onto rs plus I plus j. And you define a map in the opposite direction. Define a map from R into R mod I cross R mod j. Send any R onto I plus R comma j plus R, the obvious thing to do. And this map has kernel. This map has tensored over R. Tensored over R with j plus R. Yeah, so so this map has kernel. What is the kernel of this map? Yeah, I think I should have taken a different map, is it? Actually, I want to make sure that I plus j is contained in the kernel of the map. That is why I have defined a mapping of R into this, and this will factor through the quotient mapping of R into R mod I plus j. Okay, so is I plus j actually contained in the kernel of the map? I don't think so, because if you take an element of I plus j, little a plus, yes, why not? Yeah, it will be. So it has kernel containing I plus j. Why is I plus j contained in the kernel? Because take any element a plus b, where a is in I, b is in j, you map it to I plus a plus b tensor. Since the fact that there is a tensor product involved is actually helping us. So tensored with j plus a plus b. Now I plus a plus b is the same as no, I think I am wrong. I intersection j is in the kernel. Yeah, can you help me out? Can you help me out? So a is in I. So this is your quotient. A is in I, implies this is just same as I plus b. Yes. So this can be written as I plus b tensored with j plus a. Do you agree with this? In I, since a is in I plus a is the same as I. Now this can be written as I plus ab tensored with I plus 1. Do you agree? The tensoring is over R. Little a is a scalar in R. You can take it to that side, right? Yeah, so yeah, and this is I, so little a is in I implies AB is also in I, so this is 0 tensored with I plus 1. I didn't put brackets, I hope it is clear, and this is 0, which implies that I plus j, so this is in I, we took this one to be in I, we took this one to be in j, right? So which implies that I plus j is actually contained in the kernel, and therefore this induces a map which, oops, sorry, yeah, so the, by the way, the only thing that I defined new here, category theoretic, that's a category theoretic definition of a push out square. Probably when you see the notes you can check it out. I mean, you are not here earlier in the beginning of the session, so just check it out once. It's a category theoretic notion, nothing else. Yeah, so where did I write it? Yeah, so this, sorry, so which induces, so the mapping of R into this tensor product induces a map, a ring map, sorry, not a ring map, an R module map, R module map from R mod I plus j into the tensor product R mod I tensored over R with R mod j. Let's call this map to be G hat, and by definition it sends any element I plus j plus little r onto the element I plus little r tensored with j plus little r. Okay, so finally you check that the maps, finally check that the maps yeah, finally check that the maps f hat and g hat are mutually inverses, so that this mapping of the tensor product R mod I tensored over R with R mod j, this f hat map into R mod I plus j, this morphism is an isomorphism. The morphism this morphism f hat that we took initially is an isomorphism of R modules. Yeah, there are other ways to do so. So probably you don't know what flat modules are, but do you know what right exact or left exact functors are? Was it done? It wasn't, right? Okay, okay. So probably it won't be done. So then let's forget. But I believe exact sequences will be at least done in the course. Yeah, so option D is correct. That's fantastic. We'll solve maybe one other problem and then we'll stop. So this was another question. I mean, this is again easy. So assume R is a commutative ring. Then for any two R modules M and N, M tensored over R with N is isomorphic to N tensored over R with M. So is this true or is this false? So what do you think? Is this true or will this be false? It will be true. Okay, so what you are saying is that there is a canonical isomorphism of M tensor over Rn into N tensor over Rn. This is indeed correct, and this is actually one of the most exciting properties of the tensor product. That is, there is a kind of a braiding. This, as I was mentioning at the beginning of the session, that the tensor product is sort of an operation, right? It's an operation on the collection of modules, or more precisely, since you already know what categories are, it is something called a monoidal operation on the category of R modules. Okay, and this operation actually is a symmetric operation in this particular sense. So indeed this will be true. And how do you go about proving such a statement? You again try to exhibit an isomorphism. So you define the map from M cross N into M tensored over Rn, sorry, N tensored over Rm, M comma N will get mapped onto what? Exactly, N tensored M. And check that this is bilinear, and so R bilinearity of the mapping, this mapping induces an R linear map by the universal property of tensor products, induces an R linear map from M tensored over Rn into N tensored over Rm. Let's call this map F hat, which takes M tensored with N to N tensored with M. Now we don't even need to, of course we need to show that this is invertible, this arrow is invertible, that is, this morphism has an inverse morphism. So we need to show that this morphism has an inverse morphism, which means we need to construct a morphism in the opposite direction. But my but my point is this, that since M and N are arbitrary modules, you already by symmetry you have this map, right? By symmetry you already have a map in the opposite direction. That is, if you just switch M and N, you have a map. So G hat M tensored over Rn, which sends N tensored M onto M tensored with N, right, is a well-defined map. Module morphism, module map, module homomorphism. And clearly these two maps are inverses of each other, right? Clearly they are inverses. F hat and G hat are inverses of each other. Right? Hence F hat is an isomorphism. So this is indeed correct. This question is indeed correct. Yeah, I don't have any more energy to do other problems. I don't know if there are some problems left. Yeah, I guess I missed two problems. Let me see if one of them can be done quickly. Otherwise, we'll stop. Yeah, maybe let's stop. I'm really I have lost all my energy. Yeah, but do you also attend Ajay Prajapati's sessions? Yeah, so did he cover this problem, Qx tensored over Q with Qx? Is this isomorphic to Qx or not? Was it covered? Sorry? Oh, okay, okay. wasn't covered. Okay, so yeah, okay, so tell me something. Do you know that tensor products or modules distribute over direct sums? It is again a category theoretic consequence, but do you know that M tensored over some R with a direct sum of R modules, let's say n alpha, any arbitrary direct sum, will be isomorphic to the direct sum of, I mean, the tensor product operation and the direct sum operation commute with each other. Do you know this? Okay, okay. So this is a very category theoretic. Since you know that, so you said that you know adjoints, right? Adjoint functors. It was covered in the course, right? Yeah. So you know that you know what adjoint functors are. Ah, you don't know what. Yeah, you don't know what limits, colimits are. Yeah. So it so just so maybe so we won't be using this here, but just as an important thing to remember, always remember that you know what coproducts in a category are, right? So if you have a functor from script C into script D, from a category C into a category D, let's say F, which you know actually is a left adjoint to some functor G in the, so adjoint if two functors are adjoint, they have to be in the opposite directions, right? So if F is a functor from C into D, and then an adjoint of it will be a functor in the opposite direction. So an adjoint pair of functors F G will be a pair of functors in opposite directions. So always remember that you know what coproducts are. So always remember that left adjoints always preserve coproducts. So what I mean by this is, if you take a coproduct of objects A alpha, yeah, the right notation for coproduct should be this, alpha and lambda. If this is a coproduct of objects A alpha in the category C, then F applied on this will actually be isomorphic to yeah, if applied on this will actually be isomorphic to if the coproduct of if A alphas. Okay, this is what I'm saying. And coproducts in the category of modules is just direct sum. Okay, and do you know that the tensoring, I mean taking tensor product with a module is a left adjoint functor? Tensor Hom adjunction, are you aware of it? Okay, then it will be covered in the next week. Then I'm speaking. Yeah, so anyways, so what I'm saying is, for the particular category of R modules, so you have this functor which takes an R module M. So fix an R module N, any R module N is fixed. Now you take this functor of tensoring over R with N. So sends M to M tensored over R with N. This functor is actually a left adjoint. I mean, it has an adjoint functor. There is a functor in the opposite direction. Okay. So, yeah. So what I was saying is that this is a left adjoint, and since left adjoints preserve coproducts, so tensoring over N will actually preserve direct sums. Okay. So what, in other words, coming back to the concrete case of this tensor product functor, this is always correct for any collection of modules in alpha and for any M. Now why do I like category theory is precisely this particular reason, that you could prove this isomorphism using the universal property of the tensor product. You could give an entire algebraic proof of this. In fact, if you check a book, any book which introduces tensor products, you'll see this as an exercise, and they are using the universal property. They're proving it algebraically. But using category theory, you just need 2 lines to show this. Namely, that tensor product is a left adjoint and left adjoints preserve coproducts, and then you are done. The important thing here is that this is correct, and therefore we can use this actually to solve this problem. So this is maybe a bonus question for today. We'll end soon. This, I believe this is, I mean, I know that this won't be correct, but as Q modules is where I am. Okay, so my point is, any polynomial ring, if you take a polynomial ring, is it okay? Can I just write it as, I mean, at least as a module, can I just write it as direct sum of copies of Q? I can, right? The various terms, the various power terms. And at least as a module it is true. It is not true as a ring, but it's certainly true as a module. And therefore Qx tensored over Q with Qx is just direct sum Qx, I mean direct sum of copies of Q, right? And we know that tensor products will tensor products always commute with direct sum. So this can be written as direct sum n in n Qx tensored over Q with Q. Now you know that if A is a ring, M is an A module, M tensored over A with A is just M. So this is just isomorphic to direct sum n in natural numbers of copies of Qx, right? Isn't it? So far? Yeah. So, and finally this is isomorphic to direct sum n in natural numbers. If the isomorphisms are Q module isomorphisms, okay? So this is isomorphic to direct sum n in natural numbers, direct sum m in natural numbers Q, right? Qx can be written as a direct sum, as I said. Now direct sum of a countable direct sum of countable direct sums of Q is just countable direct sums of Q, right? So this is just isomorphic to direct sum n in natural numbers, n being just a dummy variable here, Q, which is isomorphic to Qx. Is it okay? So they are actually isomorphic. This is correct. Is it clear to you? Yeah. So yeah, my point is that you could do this again using the universal property of the tensor product, but why bother when we have something interesting like this? The tensor products actually split over direct sums. Once you have this is very powerful. We just used it. Okay. Yeah. So tensored over Q with Qx is equal to this, and yeah, and then we are done. Yeah. So that's all for today. If you have any questions, you can ask me. Otherwise, you can always email me on my email ID, which I believe I haven't written. I haven't, so I'll just write it once. I write it every week. So email is you can always email me, and yeah, that's all for today. If you don't have any questions, we can end the session. By the way, what exactly are you studying? Oh, you are a research scholar. Okay. So where are you studying? Ah, okay, okay. So you are in which year? Oh, okay, okay, okay. So all the best for your PhD. I am also a PhD student. Okay. Yeah. Okay.
So can I have that email screen?
Can you have the? Ah, yes. Just a minute. Yeah, this is my email, subhajitdas@iisc.ac.in. Yeah, okay. So see you next week.